looking at proof by induction. So we're starting off with this in our proofs. Just once we have this done, we'll have, I think, all of paper 1 done. So good, just to, might as well finish this and get used to the idea of proofs. It's probably been a while since you've looked at them. So a proof is a sequence of logical steps, and if they use the word prove, well, then you're going to have to use some algebra. Like, you can't just sub in and show that. Let's say you would have already come across proof in even just the word in patterns, where they would have said prove the sequence is arithmetic. So you can't just show that some of the sequence is arithmetic. You need to use your algebra to prove that it's all fully an arithmetic sequence. Proof by induction is kind of a strange looking proof to start off with, but it does make sense, hopefully, when I explain it, and it'll be great to revise your algebra. So don't just use it as another section. Use it as a way to revise stuff from probably 18 months ago that we looked at. You can have a look at any of the words here in case you're not sure of them, but an axiom is a mathematical statement that we accept as true. It does not need to be proven. What would be an axiom? Something as straightforward as, there's 3 points, A, B, and C. The distance from A to C is the same as the distance from A to B plus B to C. We don't need to prove any of that. We just know that it's true. As long as A, B, and C are all collinear, all on the same line. You have loads of different types of proofs which we're going to study. You've proof by deduction, proof by contradiction. We're definitely doing proof by contradiction. And then we have the one here, proof by induction. So there's the very start of the chapter here, and that's nothing to do with induction. That's to do with symbols. Do you understand what those symbols mean? Well, look, if you don't, we'll have a look at it as we're going through the book. You don't need to look at it now. So I'm going to just jump straight onto proof by induction, a divisibility proof, because I think they're just maybe a little bit easier to explain, etc. So there's 3 kind of types of proofs that we look at to do with induction, and I'm just going to take a divisibility one to start off with. So the structure of a proof by induction question is really, really important. There's marks going for how you structure it. So what the question asked me here is, they want me to prove by induction that 10 to the power of n minus 7 to the power of n is divisible by 3. And they said for all n an element of natural numbers. And our first step here is we're going to prove it true, and you have to do this for the first number you could possibly come across. So we need to actually sub in a number. And what's the smallest value of n that we could have? Well, they've told me that n is a natural number. So what's the smallest value of n that we could have? It's a 1. Step 1. I'm actually going to prove the proposition, this is what they've proposed here, I'm going to prove the proposition is true for n equal to 1. Normally, we would never do something like that. Normally, as I said there a few minutes ago, when you were doing your patterns, you wouldn't just sub in a number and prove it for part of the pattern. You might do that for yourself to see if the pattern is arithmetic. But when they say prove a pattern is arithmetic, then you need to use your algebra. So actually, this is an unusual step, or it should hopefully feel a bit unusual in comparison to what I have been saying about proofs. But the reason that we do this is because I picture proof by induction to be like a domino, like just a line of dominoes. And in order to prove it, your first step is you actually have to push that first domino. You have to just actually, like all the rest you don't have to touch. But the very first domino you will have to touch and show that it's true, in order for the rest of the dominoes to fall. Again, I'll continue explaining it as I'm going through, but that's that's what comes to mind when I'm looking at proof by induction. So that very first step is really important. I prove the proposition is true for n equal to whatever is the lowest value of n that I can have. And in this situation, it's a 1 because the smallest natural number is 1. So I go for 10 to the power of 1 minus 7 to the power of 1 gives me 3. Is that divisible by 3? Yes, it is. So you can just say yes, divisible by 3. True for n equal to 1. So that first domino I've now pushed. And if I continue doing my steps here, all the rest of them will just fall without me even subbing them in. Step 2. Step 2 is we make an assumption. We're going to assume, very unusual again in a proof that we would ever make an assumption. So we're going to assume the proposition is true for n equal to k. So we're just saying any value can be thrown in for n. Any value at all can be thrown in for n. I'm going to call it k. And I'm just going to explain that as, that means that 10 to the power of, anywhere I had an n, I'm now putting in a k, that's all. So 10 to the power of k minus 7 to the power of k, I'm going to assume that that is divisible by 7. Or, sorry, divisible by 3. Now, what's another way of saying that? To say that something is divisible by 3. You could say that 3 is a factor. And you could say, because I need to get this just to be a bit more mathsy. If you notice, I have a lot of English there, words. So 10 to the power of k minus 7 to the power of k is equal to 3 times something. So I hope that's another way of saying it. And then because we have an equation med here, feel free to mess around with your equation. Just we'll probably use this in a second at some stage. It doesn't matter how you mess around with it, just as long as, you move things around carefully. You could mess around with it a bit more. Don't really need to. It's just showing myself, what this means. Writing it a bit more mathematically, and even just showing myself that I can move it around. So step 1, you're going to have to actually push that first domino. You're going to have to actually sub it in, show that it's true for the smallest value of n. Step 2, we're doing something unusual. We're assuming the proposition is true for n equal to k. So it's kind of like that assumption. If I push the first domino, I'm assuming that if they're set up properly, the rest will fall. But I need to just explain that to people. I need to be very, very clear in my proof by induction, the different steps. And then step 3, is where I'll do most of the work. Step 3 is I need to prove the proposition is true. for n equal to k plus 1. So I'm assuming that not only will, the very first one fall, but anyone after that will also fall. So no matter what one falls, the one after it will fall also. Excuse me. I hope you can see that. It's just the light shining in. Okay. So just one more time, I just want to explain that. You can obviously just skip this little bit if you're absolutely happy with it. Step 1, you prove the proposition is true for n equal to 1. So the lowest natural number in this situation is what they said. Step 2, we're making an assumption. I'm kind of assuming that if, I've pushed the first domino, hopefully every domino will fall. And it's like, if I push that first domino, it doesn't matter what the domino is. Like, let's say I push the third domino, well, the fourth one will fall. If I push the fifth domino, well, if I push the fifth domino, the sixth one will fall, etc. So it's just trying to, I'm really, really spelling everything out here for anyone who's looking at my proof. So now, anywhere I had an n, I need to put in a k plus 1. What did I start off with? I started off with 10 to the power of n minus 7 to the power of n. So now that's 10 to the power of k plus 1 minus 7 to the power of k plus 1. Is that divisible by 3? So that's the question. That's what I'm trying to prove. Is that divisible by 3? So I said this is, this type of proof is going to be great for your algebra and your indices. So you can go to your log tables, look at your indices rules. Is there any way to rewrite any of this here? And you could write it as 10 to the power of k times 10 to the power of 1 minus 7 to the power of k times 7 to the power of 1. I didn't just write my assumption for no reason. Anywhere I see a 10 to the power of k, I can replace it with, it's equal to 3a plus 7k. So anywhere I see a 10 to the power of k, I can replace it with 3a plus 7 to the power of k. And again, that's that part times the 10 minus 7 to the power of k times the 7. I'm going to multiply this out. I end up with 30 times a plus 10 times 7 to the power of k minus 7. I'm just going to move these around. 7 times 7 to the power of k. So I just switched the order of those. 3 by 4 is the same as 4 by 3. Again, I hope you can read all that. So what I'm trying to prove is this, and here's my proof. I use my indices rules to split that up and to split this up. I go back and I use something here in my assumption. Anywhere I saw a 10 to the power of k, I can replace it with 3a, so 3 times something, plus 7 to the power of k. I then multiplied that out. So you now have 30a. And if you've 10 of something and you lose 7 of it, so you've 10, 7 to the power of k minus 7, it means you've got 3 of them. Take your 3 out in common. Is this divisible by 3? Yeah, it's 3 times something. So yes, done. This is definitely divisible by 3. So I've now proven that n equal k plus 1 is divisible by 3. I'm done. All my dominoes will fall. So if I push the fifth one, the sixth one will fall. If I push the seventh one, the eighth one will fall, etc. So they'll all fall one after another. And then you just have your conclusion. Step 4. You're going to write your conclusion. And you can just take it, here, they're all pretty similar. Sorry, no, so not this part here I did the alternative proof, so actually, you know what, I'll go over here. I did this alternative proof here. So step 4, you're just saying the proposition is true for n equal to 1. If the proposition is true for n equal to k, then it will be true for n equal to k plus 1. Therefore, by induction, it is true for all. Sorry. Therefore, it's true for all n equal to k plus 1. Or it's true for all n an element of natural numbers. Oh, stop. So, sorry about that. So what you're really doing in step 4 is you're reiterating what you did in step 2, 3, step 1, 2, and 3. So you're just bringing it all together. Just concluding it all up. Oh my God. Just try some questions on exercise, I think it's 11.3 in your book, and send on any questions that you have.